On September 6, 1976, something unexpected happened at Hakodate Airport in Japan. A Soviet pilot named Viktor Belenko landed his MiG-25 Foxbat interceptor, a plane the West feared, and defected to the United States. For years, the MiG-25 had been a mystery. NATO pilots whispered about its speed and power. American intelligence built entire reports based on blurry photos and limited radar data. They thought it was a superweapon that could outrun and outclimb anything they had. Now, they finally had the real plane right in front of them. When American intelligence officers and engineers started examining the MiG-25, they opened its fuel system to learn about its performance. What they found surprised them. Inside the cooling tanks, mixed with the fuel, was alcohol. It wasn't just any alcohol. It was high-proof ethanol, the same type used in alcoholic drinks. The Soviets were using it to cool the plane's electronics. This discovery changed everything the West thought they knew about Soviet engineering. They realized they had been making wrong assumptions about their enemy for almost 10 years. The MiG-25 Foxbat became part of the Soviet Air Force in 1970, but its development began much earlier in the 1960s. The Soviets needed a plane that could fly very high and very fast to intercept American spy planes like the U-2 and the Plan B-70 Valkyrie bomber. These American aircraft flew at extreme altitudes and speeds that existing Soviet fighters, like the MiG-21, couldn't reach. The new plane needed to climb to 80,000 feet and fly 3 times the speed of sound, Mach 3. This was a huge challenge for aerospace technology at the time. The Mikoyan Design Bureau, led by Rostislav Belyakov, was given the job. The project, called Yi-155, was very ambitious. From the start, Belyakov and his team faced problems that affected the whole design. In the 1960s, the Soviet Union couldn't make enough titanium, a strong and lightweight metal that could withstand the high temperatures of flying at Mach 3. The Americans had developed ways to use titanium for their high-speed planes like the A-12 and State Route 71, but the Soviets couldn't do the same. Instead, Belyakov's team decided to use nickel-steel alloys, especially a material called VNS2. This material was readily available and could be worked with existing Soviet equipment. However, steel was much heavier than titanium. This meant the MiG-25 had to be much larger and heavier than originally planned to achieve the required performance. The final plane weighed over 41,000 kilograms, making it one of the heaviest fighters ever built. The extra weight meant it needed more powerful engines, which generated more heat, creating a difficult cycle for the designers. The engines chosen were Tamansky R-15B-300 turbojets, huge power plants that each produced over 11,000 kilograms of thrust with afterburner. These engines were designed specifically for high-altitude, high-speed flight. At sea level, they used fuel very fast, so the plane could only fly for a few minutes. But at 70,000 feet and Mach 2.8, they performed amazingly well, pushing the massive steel plane through the thin air with great efficiency. The R-15B-300 engines were developed from earlier designs, using lessons learned from other high-speed research. Soviet engine designers had studied American jet engine development carefully, especially the Pratt and Whitney J-58 used in the State Route 71 Blackbird. They understood the advanced technology used in the J-58, but they also knew they couldn't copy it because they lacked the manufacturing capabilities and materials. So, the Soviets decided to make a simpler engine that worked very well for its specific purpose, even if it wasn't as efficient at other speeds. The R-15B-300 used a conventional design that could be manufactured with existing Soviet tools and materials. The afterburner was simple and only had 2 settings, full power or off. This made the engine easier to produce and maintain, although it gave pilots fewer options during flight. This engine design reflected how the Soviets approached aerospace technology at the time. Instead of trying to create flexible, multi-purpose systems like the Americans, they often created highly specialized systems optimized for specific missions. If the MiG-25 needed to climb to 80,000 feet and intercept bombers, then everything about its design focused on that single goal, even if it meant compromises in other areas. This approach had roots in Soviet industrial planning, which focused on meeting specific production targets and performance requirements rather than developing flexible systems. Soviet factories were set up to produce specific types of aircraft in large numbers using specialized tools and trained workers. This encouraged designs that could be made with existing capabilities rather than requiring new manufacturing processes. American aerospace companies, on the other hand, operated in a more competitive environment where versatility and technological advancement provided advantages, leading to more sophisticated but also more complex systems. This specialization extended to the plane's electronics and weapon systems. The MiG-25 carried a powerful radar, the RP-25 Smerch, capable of detecting large targets from over 100 kilometers away. The radar used vacuum tubes instead of transistors, a choice that surprised Western analysts. By 1976, solid-state electronics were standard in American military aviation, offering advantages in weight, power, and reliability. The Soviet use of vacuum tubes seemed outdated to the West, fueling the idea that Soviet technology was backward. However, this assessment missed an important point. Vacuum tubes, while bulky and less efficient, had a major advantage for the MiG-25's mission. They were resistant to the effects of nuclear explosions. Soviet planners were very concerned about nuclear war and prioritized systems that could continue to work in the electromagnetic environment created by nuclear detonations. Vacuum tubes could survive these effects that would destroy transistor-based electronics, making them the logical choice for a plane designed to fight in nuclear conditions. But vacuum tubes generated a lot of heat, especially when packed densely into the plane's nose cone. The RP-25 radar, with its hundreds of tubes, produced enough heat to damage surrounding components or even warp the plane's structure if not properly managed. Traditional cooling methods used in slower planes weren't effective at the MiG-25 speeds. At Mach 3, the incoming air became extremely hot, making it useless for cooling. Soviet engineers needed a different solution, something that could absorb and dissipate the tremendous heat while working reliably at extreme altitudes and speeds. They found their answer in a substance readily available throughout the Soviet Union: alcohol. The cooling system used high-proof ethanol circulating through a closed-loop system that absorbed heat from the radar and other electronics, then dissipated it through heat exchangers. The alcohol's low freezing point and high heat capacity made it ideal for this application, remaining liquid at extreme temperatures while efficiently transferring heat away from sensitive components. Soviet engineers calculated the required flow rates, designed pumps capable of circulating the coolant at the necessary pressure, and integrated the entire system into the aircraft's fuel and environmental control architecture. From a technical perspective, the alcohol cooling system showed considerable cleverness, using available materials and proven technologies to solve a difficult problem under severe constraints. But when American intelligence analysts discovered it 7 years later, it became a symbol of Soviet technological backwardness in the West. Viktor Belenko had been flying the MiG-25 for several years when he decided to defect. Born in 1947, he had grown up in the Soviet system and joined the Soviet Air Force as a loyal communist. His service record was excellent, and he was selected for MiG-25 training, a mark of distinction that indicated both skill and political reliability. The plane he flew represented the best of Soviet air defense capabilities, and pilots chosen for the program underwent extensive vetting to ensure their ideological commitment. Yet, beneath his facade of Soviet loyalty, Belenko harbored growing doubts about the system he served. He had access to forbidden Western radio broadcasts and saw the differences between official propaganda and the reality of life in the Soviet Union. He also had access to information about Western life through his position, information that contradicted what he had been taught about capitalist decay and socialist superiority. Planning his defection took months. Belenko couldn't just fly away. MiG-25 flights were tightly controlled, with ground controllers monitoring every plane's position. Deviation from assigned flight paths triggered immediate alerts, and Soviet air defense forces would shoot down a rogue aircraft, even if flown by their own pilot. Belenko needed a flight plan that would give him enough time to cross into foreign airspace before controllers could react. He studied maps, calculated fuel requirements, and waited for the right training mission. That mission came on September 6, 1976. Belenko was assigned a routine high-altitude intercept practice over the Sea of Japan. Once airborne, he descended to low altitude using terrain masking to avoid radar detection and turned toward Japan. The MiG-25, designed for high altitudes, handled poorly at low levels, making the flight difficult. Belenko fought the aircraft, pushing the engines to maximum dry thrust. Behind him, Soviet radars had lost track of him, and controllers assumed he had crashed. Belenko successfully penetrated Japanese airspace and approached Hakodate Airport. His fuel gauges showed critically low levels. The MiG-25's engines had consumed nearly all available fuel during the low-altitude flight. He had no choice but to land immediately, regardless of proper procedures. The landing was legendary. Belenko brought the massive interceptor down on Hakodate's civilian runway without communication with the tower, touching down at very high speeds. The MiG-25 used nearly the entire runway before coming to a stop, its brakes smoking. Japanese airport personnel watched in disbelief as the Soviet fighter sat on their runway. Only when security vehicles approached did Belenko shut down the engines, climb out, and surrender, requesting political asylum in the United States. He had become the biggest intelligence prize of the decade. American intelligence agencies learned of the defection within hours. They recognized the opportunity. The MiG-25 represented the biggest intelligence gap in their understanding of Soviet air defense. For nearly a decade, they had built reports and tactics based on assumptions about the plane. Now, they had the actual aircraft for detailed examination. But there was a diplomatic problem. The MiG-25 had landed in Japan, not American territory. Japanese officials, while allied with the United States, had diplomatic relations with the Soviet Union and couldn't simply hand over the plane. The Soviets immediately demanded the return of both pilot and aircraft, claiming Belenko was disoriented or drugged. Japanese officials decided on a compromise. Belenko could go to the United States, but the aircraft would be examined by Japanese authorities before any decision about its future. This gave American intelligence exactly what they needed. Japanese officials agreed to allow American technical experts to participate in the examination, giving the CIA and Air Force complete access while maintaining the appearance of Japanese control. Within 48 hours, American transport planes brought specialized equipment and personnel to Hakodate. The team included engineers, technical specialists, and experts from American aerospace companies. They arrived with testing equipment, measurement tools, cameras, and detailed checklists prepared over years of gathering intelligence on the MiG-25. The examination began immediately. Every component was measured, photographed, and analyzed. Material samples were tested, engines were partially disassembled, and the radar was powered up and tested. Every major system underwent intensive scrutiny. American engineers discovered that the plane was even heavier than they had estimated, using relatively simple construction techniques like hand welding. This suggested that Soviet production involved more manual labor than comparable American aircraft, possibly indicating limitations in manufacturing automation. The engines were particularly interesting. They used construction techniques that American engineers had abandoned in the 1950s, including welded steel components instead of lighter titanium. Yet, despite these apparently crude methods, the engines performed remarkably well, generating huge thrust at high altitudes while maintaining acceptable reliability. The examination showed that Soviet engineers achieved competitive performance through brute force engineering, accepting weight and complexity that American designers would consider unacceptable. This pattern appeared throughout the aircraft, choosing proven, robust solutions over elegant efficiency. The flight control system used mechanical linkages instead of hydraulic or fly-by-wire systems, adding weight but ensuring reliability. The fuel system used simple pumps and valves, making it less efficient but easier to maintain. But nothing generated more interest or misunderstanding than the discovery of alcohol in the cooling system. When technicians first accessed the environmental control system, they expected to find specialized aerospace coolants. Instead, they found ethanol, the same substance used in alcoholic beverages, mixed with other compounds. The initial reaction among American engineers was disbelief followed by amusement. The idea that Soviet designers used common alcohol to cool a sophisticated fighter seemed to confirm Western stereotypes about Soviet technological backwardness. Jokes circulated about Soviet pilots drinking the coolant. These reactions missed the engineering thinking behind the solution. Ethanol possesses several properties that make it near ideal for aircraft cooling. It can absorb more heat than water. Its freezing point is far below water's, and its lower boiling point allows for more efficient heat transfer in a properly designed system. Most importantly, for Soviet designers, ethanol was readily available, easily produced, and required no complicated manufacturing. The decision to use ethanol reflected a broader Soviet design philosophy that American engineers were only beginning to understand. Soviet aerospace designers operated under different constraints than their American counterparts. They had unlimited labor, but limited automation, could produce basic materials like steel but struggled with advanced alloys, and had strong theoretical engineering expertise but limited ability to manufacture precision components at scale. Within these constraints, they developed design approaches that maximized available resources while minimizing dependence on capabilities they lacked. Using alcohol as a coolant exemplified this perfectly. It worked effectively, used available materials, required no complicated manufacturing, and could be maintained with minimal training. The technical specifications of the cooling system revealed sophisticated engineering within its apparent simplicity. The ethanol coolant circulated through channels machined into aluminum heat exchangers mounted directly against the radar's vacuum tubes. Soviet engineers had calculated the required flow rates and designed pumps capable of maintaining sufficient pressure while operating reliably at extreme altitudes. American aircraft of the same era typically used more sophisticated but complex cooling approaches. The F-14 Tomcat, for example, used a liquid cooling system with specialized synthetic coolant and sophisticated flow control valves. This system worked excellently, but required multiple specialized components and regular maintenance with specific tools and equipment. Soviet maintenance personnel in remote areas often lacked access to such specialized equipment. The MiG-25's cooling system, by contrast, could be serviced with basic tools and commonly available fluids. This maintainability provided significant operational advantages that pure performance specifications didn't show. American engineers, trained to prioritize efficiency and performance, initially struggled to appreciate this alternative design approach. They had been taught that good engineering meant pushing the boundaries of material science and finding the optimal solution. The Soviet method of accepting material limitations as fixed constraints and then optimizing within those constraints seemed backward. But as the examination of the MiG-25 progressed, a more complex picture emerged. The plane, while crude by American standards in many aspects, actually performed its intended mission extremely well. It could climb faster than any American interceptor, and its radar could detect targets at ranges comparable to American systems. The MiG-25 worked, and it worked reliably in the harsh operational environment of the Soviet Air Force. This realization forced a reassessment of Soviet capabilities. American intelligence had spent a decade assuming the MiG-25 represented a Soviet attempt to match American technological sophistication using similar designs and materials. The actual aircraft revealed that Soviet designers had never tried to match American approaches. Instead, they had developed their own distinct methodology, one that prioritized operational effectiveness over technical elegance, reliability over refinement, and predictability over performance optimization. This allowed them to field competitive systems despite operating under severe constraints. The alcohol cooling system became symbolic of this broader revelation. What initially appeared to be a crude solution actually represented sophisticated engineering thinking adapted to specific constraints and requirements. This discovery influenced subsequent American intelligence assessments of Soviet military technology. Prior to the MiG-25 examination, analysts tended to either overestimate or underestimate Soviet capabilities, depending on their biases. The MiG-25 revealed that both positions were wrong. Soviet systems were neither technological marvels nor crude copies of Western designs. They were distinct products of a different engineering culture, one that achieved competitive results through alternative methods. Understanding this required considering how systems performed in their intended context under realistic conditions. The cooling system discovery had specific tactical implications as well. American specialists had assumed that Soviet radars using vacuum tubes would be vulnerable to certain jamming techniques. The realization that these radars were actually resistant to EMP forced a rethinking of electronic warfare tactics. Similarly, the discovery that many Soviet aircraft systems used simple, robust components that could be maintained with basic tools suggested that Soviet forces might be more resilient in sustained combat than previously thought. These insights directly influenced American defense planning. American planners had justified huge spending on advanced fighter aircraft by pointing to the supposed superiority of Soviet interceptors like the MiG-25. The examination revealed that while the MiG-25 was formidable in its specific role, it had severe limitations that made it less threatening than estimated. It was optimized for high-altitude interception, had poor maneuverability at low altitudes, and had a very limited range. This realization should have led to more balanced assessments of air superiority, but instead, it often reinforced existing positions. The intelligence collected from the MiG-25 examination directly influenced several major American defense programs. The realization that Soviet radars used vacuum tubes prompted the U.S. Air Force to invest in new jamming techniques. The discovery that Soviet aircraft construction relied heavily on manual fabrication influenced estimates of Soviet aircraft production capacity, leading to higher projected numbers of Soviet interceptors. These revised estimates then justified increased American investment in air superiority fighters like the F-15 and F-16. Viktor Belenko provided detailed information about Soviet air defense procedures, training methods, maintenance practices, and operational doctrine. His testimony confirmed and expanded upon the technical intelligence gathered from examining his aircraft, offering context about how the MiG-25 fit into broader Soviet defensive strategy. Belenko eventually became an American citizen and lived quietly in the United States. His defection remained one of the most significant intelligence coups of the Cold War. The Soviet Air Force never forgot his betrayal. Security procedures for MiG-25 pilots were dramatically tightened, with increased political indoctrination and closer monitoring of personal behavior. The defection had demonstrated that even carefully vetted pilots could not be entirely trusted. The legacy of the MiG-25 examination extended far beyond the technical data collected. It represented a turning point in American understanding of Soviet military capabilities, forcing a shift towards a more nuanced appreciation of alternative design philosophies. This shift influenced how American intelligence analyzed subsequent Soviet weapon systems, encouraging analysts to consider operational context and design constraints rather than simply comparing performance specifications. In retrospect, the discovery of alcohol in the MiG-25's cooling system reveals as much about Western analytical frameworks as it does about Soviet engineering practices. The initial reaction of amusement reflected deep assumptions about technological progress and engineering sophistication. Soviet engineers operating under radically different constraints had developed an alternative framework that prioritized reliability and predictability while accepting compromises in weight and efficiency. Both approaches could produce effective military systems, but they did so through fundamentally different paths. The Cold War arms race is often portrayed as a simple competition between American quality and Soviet quantity. The MiG-25 examination revealed this to be overly simplistic. Soviet systems were not simply crude copies of Western designs. They represented distinct engineering solutions to similar problems. Understanding this required moving beyond superficial assessments toward deeper analysis of how systems functioned in their intended context. The alcohol cooling system exemplified this alternative approach, using available materials and proven technologies to solve a difficult problem effectively and reliably. This discovery challenges comfortable assumptions about technological progress. There are multiple paths to effective solutions, shaped by available resources, manufacturing capabilities, operational requirements, and cultural factors. Soviet engineers, working within constraints American engineers would consider crippling, nonetheless created a functional, effective interceptor that performed its mission successfully for decades. The story of the MiG-25's alcohol cooling system ultimately tells us that engineering excellence comes in multiple forms. The Soviet engineers who designed that system were not backward. They were highly skilled professionals working within specific constraints to solve difficult problems, and they succeeded. Recognizing this requires humility about our own assumptions and a willingness to consider that our way of solving problems may not be the only valid approach. This lesson remains relevant today as we continue to assess technological competition between nations with different resources, capabilities, and engineering cultures.